nuclear magnetic resonance by NMR spectroscopy. তো এর মধ্যে হচ্ছে nuclear magnetic resonance technique which is based on the absorption in the radio frequency ranges 4 to 900 megahertz by nuclei of the atoms, and the proton nuclei nuclear magnetic resonance spectroscopy is one of the most powerful tool for elucidating the number of hydrogen or proton in the compound, and it is used to study a wide variety of nuclei, 1H, 13C, 15N, 19F, and 31P, etc. Then next is the if the external magnetic field is applied, the number of possible orientation calculated by is 2I plus 1, and the hydrogen has spin quantum number I equal to half, and possible orientation is 2 into half plus 1 equal to 2. So it's 2 plus half minus half. So here energy field strength B naught, I equal to এখানে I by 2, spin state I equal to minus half B, spin state এখানে যেটা আছে সেটা হচ্ছে plus I by 2, এখানে হচ্ছে alpha. Then principle of NMR spectroscopy, the theory behind the NMR comes from the spin of the nucleus, and it generates a magnetic field without an external applied magnetic field. The nuclear spins are random in directions, but when an external magnetic field B naught is applied to the sample, the spin present in the nucleus gets aligned in either with or against the directions of the applied magnetic field. Then the applications of the external magnetic field results in the generations of the energy difference in del E between the excited state and the ground state. The transfer of the energy takes place at the wavelength which is equivalent to the radio frequency. When the spin comes back to the initial ground state, it emits the absorbed radio frequency, and this emitted the radio frequency gives the NMR signal of the corresponding nucleus, and the emitted radio frequency is proportional to the magnitude of the applied magnetic field, V equal to gamma B naught by 2 pi. এখানে হচ্ছে B naught মানে কি external magnetic field experienced by proton, gamma equal to the magnetogyric ratio, the ratio between the nuclear magnetic moment and the angular moment, and then intensity is high here, and frequency is upfield and downfield. Then deshielded nuclei and the shielded nuclei, deshielded nuclei and shielded nuclei, and TMS, this thing. Then NMR spectrum is a plot of intensity of NMR signals versus magnetic field frequency in reference to TMS. Then nuclear radiation detector, nuclear radiation detector. So nuclear radiation detector are required, all the nuclear radiation detectors are required in all the major fields of the nuclear science and technology, and they fall into two principal categories: single element detectors and imaging detectors. Single element detectors can be classified into 4 types based upon their physical mode of operation. The nuclear radiation is a generic term, refers to the large variety of the radiation resulting from the nuclear processes. Then the major type of scintillation counters, gas ionization detectors, ionization chambers, proportional counters, Geiger-Müller counters, then semiconductor detectors, and then chemical detectors. Then radiation detector applications, scientific and technological areas where the nuclear radiation detectors are required: nuclear power, radiation technology, biological and medical, and nuclear and physics research. Then radiation detectors এর মধ্যে যেটা আছে সেটা হচ্ছে nuclear radiation detectors can be divided into two distinct domains, namely single element detectors and imaging detectors. Imaging detectors are primarily of use in the fields of the nuclear physics and of the medicine and biology, and single element detectors dominate both numerically and in importance. Then single element detectors may be divided into four major classes. On is the scintillation counter. So this is, there is the X-ray and optical coupling, then photo multiplier, power supply, then amplifier, then pulse height analyzer, then gas ionization detectors. Here gas ionization detectors and schematic diagram and the voltage chamber and then charge per ion. Here you can see. Then semiconductor detectors and semiconductor detectors here, then amplification analyzer, power supply, radiation crystal, conduction band and then valence band. Then chemical detectors. Then chemical detectors এর মধ্যে যেটা আছে সেটা হচ্ছে যে photographic field glass or crystal radiation darkening, if centers etc, dye reactions and then fluorescent. Then radiation detector requirements: high sensitivity, energy resolution capability, high speed, then radiation discrimination and the ability to detect the neutrons, and the inclusion of the neutron detection is without doubt a logical misdemo de demenon. However, the subject is of the great importance and should be singled out for emphasis. And imaging detectors, area imaging, photographic and the scintillation counter scanning, track imaging, Wilson cloud chamber, bubble chamber, nuclear emulsion, then spark chamber, then scintillation track imaging. Then conclusion: it is clear that the development of the nuclear radiation detectors has a long road ahead of it before the field is complete. Even at the present rate of development, it will be many years before the practical detectors will be able to accomplish all that can be theoretically predicted for them, and many advances in both single element and imaging detectors will come through appreciations of the semiconductors and solid state principles to the detector field. Then electron spin resonance spectrometer, ESR is an acronym for electron spin resonance spectrometer, is also known as the EPR, electron paramagnetic resonance spectrometer. And ESR is a method for observing the behavior of the electrons within a suitable molecule and for analyzing various phenomena by identifying the neutron in environment. ESR measurements afford the information about the existence of the unpaired electrons as well as quantities, type, nature, environment and behavior. ESR is actively being applied in pharmaceutical and agricultural basic research and is widely used for various applications such as production lines for semiconductors and coating, as well as in the clinical and medical fields such as the cancer diagnosis. Then ESR spectrometer composition, then computer in instrument operation and the data processing. Microwave unit: the microwaves introduced into the cavity oscillate and the signal is detected. Then magnet: a strong magnetic field of the several thousands gauge is applied to the unpaired electrons and the spin energy levels are separated. Then spectrometer: the microwave absorption by the unpaired electrons is amplified and recorded. Then working on the electron spin resonance, ESR, it is absorbed, it is this absorption that is monitored and converted into a spectrum. The great majority of the EPR measurements are made with the microwaves in 9000 to 10,000 megahertz, 9 to 10 megahertz range. And EPR spectrum can be generated mostly by keeping the photon frequency fixed while varying the magnetic field incident on a sample. A collection of paramagnetic centers such as the free radicals is exposed to microwaves at a fixed frequency. By increasing an external magnetic field, the gap between the energy state and the unwinded and is winded until it matched and the energy of the microwave. At this point, the unpaired electrons can move between their two spin states and since they are typically are more electrons in the lower state due to the Maxwell Boltzmann distribution, there is a net absorption of the energy. Then XPS principles and instrumentation belongs to the groups of the surface and surface analysis method, irradiating the samples with low energy equivalent 1.5 kilo keV. Then photoelectric effect is indeed then electron spectrometer with high resolution records the energy spectrum of emitted photoelectrons. Available vacuum conditions are required for XPS experiments to assess the photoelectron transport to the analyzer. Also avoids the recontaminations of the clean samples. And principles এর মধ্যে যেটা আছে সেটা হচ্ছে কি সারফেস অ্যানালাইসিস বাই দ্য এক্সপিএস ইনভলভস দ্য ইরিডিয়েশনস অফ দ্য স্যাম্পল বাই লো এনার্জি and the mono energetic X-rays and the subsequent analysis of the energy of emitted electrons, and typically use the X-rays are K alpha lines of magnesium and aluminum, and the penetration depth of these photons in the solid is limited to a few microns, and these interactions take place between the incident photons at the surface atoms, leading to the photoelectric emissions of the electrons. Then the instrumentations of the XPS system can be explained using the experimental setup showing monochromatic XPS system here. So this is the figure. Then principle of the X-ray. X-rays are a type of photoelectromagnetic radiation. Just like the visible light, there are three criteria that must be met to allow the electromagnetic radiation to be used for the imaging purpose: ability to create to the electromagnetic radiation and the wavelength required, and ability to focus the radiation on a particular area, and ability to detect the radiation once it has passed through the object. Then the radiation is created when the electric current is generated from a high voltage generator, and this causes the electrons to boil off from the cathode end of an X-ray tube assembly, and these electrons are emitted from a filament on the cathode rushed towards a target material known as an anode, and this process is known as the thermionic emission, and this is the figure. And then principle of the X-ray: the electrons emitted by the cathode rush towards the anode, which holds a disc made of the tungsten. When the electrons collide with the tungsten, several interactions occur at the atomic level. One of these interactions cause the electrons to be expelled from the outer orbits of the atoms, releasing a X-ray photon. Then principle of the X-ray মধ্যে যেটা আছে সেটা হচ্ছে কি the production and the properties of the X-ray: electromagnetic radiation, X-ray tube, X-ray spectrum, properties of the X-rays. Then interactions of the X-ray with the matters, then absorption and attenuation, Box's law, and diffraction, commotion, scattering, the photoelectric effect. Then X-ray detection techniques এর মধ্যে film based on detectors, scintillation detectors, solid state detectors, and then gas detectors. Applications of the X-ray detectors and the laboratory use: then X-ray diffractions, X-ray effluence spectroscopy, then X-ray absorption spectroscopy, X-ray crystallography. So this is the thing. Then instrumentation of X-ray spectroscopy. Then components of the X-ray spectroscopy: X-ray generating equipment, X-ray tube, and collimator, monochromator, and detector. Then X-ray generating equipment or X-ray tube: X-ray can be produced through the X-ray tube, and it is a vacuum tube that utilizes an extremely high voltage to speed up the release of the electrons by cathode's hot surface to a very high speed, and the electrons of high velocity interact with a metal object and anode, and this creates the X-ray. Monochromator crystals partially transfer an unpolarized beam of X-rays, and the principal functions of the monochromator is to isolate and transmit a small part of the optical signals from a greater spectrum of the wavelength that are available at the point of input. And type of monochromator: metallic filter type and diffraction greater type. Then X-ray diffractors এর মধ্যে যেটা আছে সেটা হচ্ছে the most commonly employed detectors include solid state detectors and the scalentation detectors. Then solid state detectors, the semiconductors charge carries the comprises holes and electrons radiations that strike the semiconducting junctions, creates a electron hole pairs when it passes through it, and the electrons as well as the holes get eliminated under the influence of the electronic field. The appropriate electrons are able to collect the charge within the forms of a pulse. And the scalentation detectors comprises a instrument called the scintillator, and like the PMT or photo multiplier tubes, which converts the light into electrical signals, and it made up of the evacuated glass tube with the photocathode, and it is typically comprises of between 10 to 12 electrodes referred to as the diodes and anodes. And the photocathodes emits the electrons that are attracted by the first diode and then accelerate to the kinetic energies that are equal to the differences in the potential between the photocathode and the first diode. When the electrons strike the first diode, first electrons are released from the diode per electron that hits it, and these electrons are ejected by the second diode then onto the anode, and total amplification of the PMT is the result of the individual amplification that it occurs at each diode. Basic components of the instrumentation for the X-ray স্পেকট্রোস্কোপির মধ্যে যেটা আছে সেটা হচ্ছে the electric power voltage stabilizer, high voltage generator, X-ray tube, slit collimator, then specimen detector, then এখানে কারেন্ট স্টেবিলাইজার আছে একটা, দেন এমপ্লিফায়ার, স্কেলার, দেন প্রিন্টার, দেন রেড মিটার, and then recorder. Then basic components of the instrument of the X-ray spectroscopy. Then X-ray diffractors. X-ray diffraction. What is X-ray diffraction? The atomic planes of a crystal cause an incident beams of the X-rays to interfere with one another as they leave the crystals, and the phenomenon is called the X-ray diffraction. And the principles of the X-ray, in antecedent X-rays and the diffractory X-rays, then atomic scale crystal lattice planes, Boch's law of diffractions, and then X-ray diffractors. Then X-ray absorption spectroscopy, then principal instrumentation and application. Then X-ray absorption spectroscopy has become an essential tool while studying the morphological details of the chemical substances. X-rays are short wavelength electromagnetic radiations. They are used to in various ways to analyze the structural arrangements. Then principal X-ray absorption spectrometry. X-ray spectrometry works on the principles of the excitations of the core electrons that are orbiting in the lower shells. As the electron absorbs the X-rays, it becomes excited and jumps to a higher level, and the X-ray regions used ranges from 1 to 100 nanometers. When X-rays interact with the electrons, it excites the electron to the higher level, and energy absorbed by the electrons has a characteristics value for each element. One can distinguish with the X-ray absorption spectrum. Then instrumentation of the X-ray absorption spectroscopy, then electron beam, then X-ray, heavy metal monochromators, grating crystals, then X-ray detectors. Then applications of the X-ray absorption spectroscopy. X-ray are nowadays used in almost every scientific study to analyze the structure, and in medical treatment, X-ray imaging is used to find the bones fracture and cracks, and it can detect the elements specifically based upon their core levels, and the graphs is well separated and have the high resolutions, and it can also be used to determine the structure and the orientations of the solids in the metal ores. Then X-ray fluorescent spectrometry principle. XRF spectrometry can determine the elemental composition of a wide range of materials including solid, liquid, and powders, and XRF spectrometry is widely used in the fields such as the metallurgy, mining, environmental science, archaeology, among others. Then XRF spectrometry is a non-destructive analytical techniques used to determine the elemental composition of the material, and XRF spectrometry can provide both qualitative and quantitative analysis of the elements present in a material, and X-ray spectrometry can be used to analyze the elements ranging from sodium atomic number 11 to uranium atomic number 92. Then X-ray spectrometry can be performed on site, making it a convenient method for field work and real-time process monitoring in the industries. And X-ray analysis can provide rapid results with some instruments capable of analyzing a sample in just a few seconds. Mm, then X-ray analysis can be used to identify the trace elements in a sample even at a concentrations as low as per million ppm, and X-ray analysis can be used to determine the thickness and the composition of the thin films and the proteins. So these are the figures you can see here.